Hello everyone, my name is Mitra, and for this breakthrough challenge I have chosen the topic quantum entanglement. Not many people know about quantum entanglement because it's a developing concept. But yeah, we have so many experimental proofs coming up that are exciting science nerds like me and you. Well, before I get into that, I will introduce to you about quantum mechanics if you are new to it. Well, quantum mechanics, we use it to understand the behavior of subatomic particles like the electrons, the protons, neutrons, and even the photons. Well, we cannot use the classical mechanics like the Newtonian mechanics and his equations because they behave spooky. The subatomic particles behave spooky. So new mathematics was developed, mathematical tools like Schrödinger's equations and many more complex ones. I'm not going to get into that. So basically quantum mechanics is trying to understand subatomic particles, right? So researchers at Griffith University's Center for Quantum Dynamics actually came up with an excellent experiment to prove quantum entanglement and its effect, that is a wave function collapse. So I will tell you the definition for quantum entanglement. Try to decipher it. Quantum entanglement is a physical phenomena that occurs when pairs or groups of particles are generated or interact in ways such that the quantum state of each particle cannot be described independently. Instead, a quantum state may be given for the system as a whole. Okay, so if you consider two particles A and B, they constitute an entangled system. Just consider. So I can say that the overall quantum state or like overall spin, okay, it's a good analogy to think of, is zero. But I cannot say that, okay, maybe A have this and B may have this. I will not say that A will have spin up and B will have spin down. I can say it may have spin up and may have spin down. I cannot have definite answer because I will give you some probability, probability densities and stuff like that are there. I can say that these are the probable values that A can give. These are the outcomes A can give. But I cannot tell you a definite value, the definite probable value. But for the system as a whole, I can say that yeah, it's zero. Okay, so spin here I do not mean that they are literally spinning or something, but it means their angular momentum or their spatial orientation though, or the phase of that particle constituting that matter wave. So to understand this, just think of a spinning wheel which is made out of 7 colors with gear. So if I spin it fast enough, you would know that it'll pretty much appear like a white disc, right? And not having 7 colors or something. But once if I try to stop it using my finger, I may be stopping at one color, maybe yellow or red. So I am actually forcing that disc to give me one outcome out of the 7 probable outcomes. So for every color, the probability is 1/7. But just because I'm making a measurement, I'm getting one finite value, one particular value. I'm not getting so many random values. But this decision which is taken by, I'm actually forcing that wheel to make a decision. So this decision which is made by the wheel is instantaneous and random. It's not that it will only give yellow. It may give any other red or indigo or purple, anything, right? So same with these particles, like when I'm trying to make a measurement on them, it's just random and it's very instantaneous and it's not dependent on anything, right? But yes, the other entangled particle, so if A and B are there, if I am having set of probable values that may be the outcome of A when I make a measurement, when I'm making a measurement, I'll actually get one of those probable values. It's not that it will give me only certain definite values. It will give me some random instantaneous. I'm actually forcing that particle to give me one particular value, and that is known as wave function collapse. This feature is known as wave function collapse. So why is it spooky for Einstein? Because if say I detect if I measure A and the spin comes out to be spin up, then even without making measurements on B, and if those two particles are entangled, and even without making any measurements on B, I can say that it has spin down. That is quite instantaneous. Like even without making any measurements, I come to know it. How? Because they're entangled. And here comes another question. Did information pass faster than light between them, or how did I even affect the outcome of B without even measuring it. This disturbed Einstein, right? How can, stuff, information seems big. Information travel faster than light. So he came up with some other explanation which was quite consistent also. It's, yes, nice and good. So he said that these particles are not entangled, but they are having some hidden information with them, but we just do not know it, right? We are not able to find it out, but they have this information within themselves and they are somehow connected. So that's why, when you try to measure that, it comes out to be, it's like, coincidence. So to understand his explanation, think of this, okay? So you have a pair of socks, and the one you wear on right and left, both of them. So I have these socks and I put one in box A and another in box B, and these boxes are similar, okay? So if I give box A to a girl and a box B to a boy, and if the boy goes to some other planet like Jupiter or Mars or somewhere else, and the girl stays on on Earth itself, and if I tell them to open the box, so if I tell the boy first to open the box, and he finds out that the sock in his box is the one which would be worn on the left leg. So without even going back to Earth, he can say that the girl has the right sock. That's instantaneous, right? So this is not because the particles are entangled, but they are somehow connected. Obviously, they are a pair of socks. It's that they have this information, the hidden information that these observers did not know, but I knew it, but I didn't tell them, right? So these observers did not know it, but when they make that measurement, that is when they made that measurement of opening the box and looking at the sock, they come to know the state or the pair, which is like the sock which is with the girl. So this is what Einstein explained. Well, it was quite satisfying. So this is what he and two more buddies of his came up with. So this was described by Albert Einstein and Boris Podolsky and Nathan Rosen in a 1935 paper, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? So this was famously known as the EPR paradox, and simply the whole paper meant that maybe entanglement was wrong, or maybe previous ideas about quantum mechanics had some adjustments that we had to make. It had to be refined. It was not complete according to him. But not so, because as I told you, a group of researchers have actually proved single particle quantum entanglement and the effect. So what they did is they send beam of electrons through a beam splitter. So what happens is 50% of them go to lab A and 50% to lab B. So this is what happens. So what the researchers at lab A and lab B did was they tried to detect a photon and studies wave properties using a homodyne detector. This homodyne detector is an instrument to study waves and its properties, right? It's one complicated instrument that which will detect the photon and also identify its quantum state. So what happens is that lab A tried to look for its photon and measure its phase, and so did lab B. So when lab A detected a photon, at that instant lab B didn't. And same thing happened at lab B. When lab B researchers, they detected a photon, at that instant lab A detectors did not find any photon there. And whatever quantum state that lab B photon had depended on what lab A was giving. So it was affected by some other measurement which was done in some other lab. So this is what exactly you would get if a single split photon were entangled. So what this guy was like, what this professor, the Howard Weizmann and his team actually demonstrated wave function collapse, and obviously it's real, isn't it? Like the measurement made on A is affecting B. So through these different measurements, you see the wave function collapse in different ways, thus proving its existence and showing that Einstein is wrong. So yes, they proved quantum entanglement for single particle, and they proved that the wave function collapse effect is real and that Einstein is wrong. three observations made. So I hope in this video you people understood what is quantum entanglement and what is the effect of it, and that is wave function collapse, and how in that experiment performed by these researchers helped them to prove the effect of wave function collapse. So thanks a lot for watching this video. Bye bye.